For the simplification of Boolean algebra, we already covered algebraic method. Now we will start with the Kernel Map method. The Kernel Map provides a systematic method for simplifying Boolean expression, and if properly used, will produce the simplest stop or pause expressions. This method is widely used for the simplification of Boolean expression. This method is very effective method for 2, 3, 4, and even 5 variables. First of all, let us see the mapping process for different number of variables. First of all, let us see 3 variable mapping. Suppose we have 3 variables A, B, C. The mapping can be done. We can have 2 variable in one side and 1 variable in another side. Using 2 variables, we will have 4 combinations. 0, 0, 0, 1, 1, 0, 1, 1. We know this. That's why we will make 4 rows to represent that. And using 1 variable, we can have 2 combinations, either 0 or 1. So value of C can be written here 0 or 1. C can have value 0 or 1. AB can have value 0, 0, A equal to 0, B equal to 0, A equal to 0, B equal to 1. Now, while placing the values for rows or columns, you need to consider that from one value to another value, you need to have only one change. That's why you cannot write 1, 0 here. We'll write 1, 0 here and 1, 1 here. Remember, this 1, 1 represents decimal value 3. This 1, 0 represents decimal value 2. This 0, 1 represents decimal value 1. And this 0 represents decimal value 0. So for 2 variable case, this will be 0, 0, 0, 1, 1, 0, 1, 1. This will be the case. Again, for 3 variable mapping, if someone wants to map in this fashion, that you will put 1 variable in one side and 2 variable in another side, that means A, B, C, unlike this one. So here for BC case, there will be 4 column, and for A, there will be only 2, which will represent all the possible values for A. So for one variable, the possible values can have 0 or 1. But for BC, there are 2 variables. The possible values will be 0, 0, 0, 1, 1, 0, 1, 1. You need to place the values in this fashion. Next, let's see 4 variable mapping. Suppose the variables are A, B, C, D. For 4 variable mapping, we'll take A, B in one side and C, D in another side. So in each side, we have 2 variables. That's why we need to draw 4 columns and 4 rows. This will be 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1. Now, using 3 variables, how many combinations can we have? We can have 8. That's why we have 8 small rectangulars. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Here 1, 2, 3, 4, 5, 6, 7, 8. But using 4 variables, how many combinations can we have? We can have 16 combinations. And here we have 16 smaller rectangle. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now let's see the names of each smaller rectangle. First of all, what is the address or what is the name of this rectangle? In min-term form, here we can see A equal to 0, B equal to 0, and C equal to 0. This rectangle represents the values of A, B, C with 0, 0, 0 respectively. The name of this rectangle in terms of min-terms can be written as A prime, B prime, C prime. Again, in terms of max term, when A equal to 0, B equal to 0, C equal to 0, the name of this rectangle becomes A or B or C. For the time being, we'll represent all the names in terms of min terms. First, let us understand the names in terms of min terms form. Later on we'll go with the max term. So this is a prime, b prime, c prime, 0 0 0. This is a prime, b prime, c, which means 0 0 1, 0 0 1, a equal to 0, b equal to 0, c equal to 1. This is 0 1 0, this rectangle. So this name will be a prime, b, c prime, and this rectangular will be a prime, b, c. 1 0 0, this is 1 0 0, a, b prime, c prime, a, b prime, c, a, b, c prime, finally a, b, c. Again, in terms of value, we can write a equal to 0, b equal to 0, c equal to 0. This rectangle represents a equal to 0, b equal to 0, c equal to 1. This rectangle represents a0, b1, c1, a0, b1, c1, a0, b1, c0. This represents 1 0 0, 1 0 1, 1 1 0, 1 1 1. If you want to represent this in terms of decimal number, so this is 0 1 2 3 4 5 6 7. 1 1 1 means 7 in decimal. Again, for 4 variables case, this represents 0 decimal numbers, which is 0 0 0 0. This represents 1 decimal, 0 0 0 1. This represents 2 3. So 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. 15 means 1 1 1 1. So we have 1 1 and 1 1. This rectangle represents 1 1 1 1. If you are asked the name of any arbitrary rectangle, for example, what is the name of this rectangle, or what is the value of different variables in this rectangle, so you'll say 1 0 0 1. So this represents 1 0 0 1, which has decimal value equal to 9. Okay, now if a equal to 1, b equal to 0, c equal to 0, d equal to 1, in terms of min terms, this can be represented as a, b prime, c prime, d. And in terms of max terms, we can write a prime plus b plus c plus d prime. Next, we'll see the concept of adjacent cell. In short, the cells that are placed side by side, they are adjacent cells. Let me clarify your concept. Suppose these two cells are adjacent, this cell and this cell. Again, these two cells are adjacent, this cell and this cell. We can say these two cells are adjacent. So they are adjacent cells. If we make a cylinder out of this box, suppose if you want to make cylinder, then this line and this line will be connected. So in that fashion, we can say these two cells are also adjacent. These two cells are also adjacent. These two cells are also adjacent. But we cannot have two adjacent cells diagonally. Diagonal rectangles are not considered as adjacent cells. Now, while considering the adjacent cells, how many smaller rectangles should be taken in one group? We can take two adjacent cells side by side, or 4 or 8. We cannot take 3 or 6 adjacent cells. So while considering adjacent cell, we must take the number of adjacent cell having 2 to the power x values, where x equal to 0, 1, 2, in this way, any integer number. So we can take either 2 to the power 0, that means 1 cell, single cell, 2 to the power 1, 2 cell, 2 to the power 2, 4 cell. So 4 cells can be taken together, or 8 cells can be taken together, or 16 cells can be taken together if they are adjacent. Let me show you the concept of 4 adjacent cells. Here, these 4 cells are adjacent. This is clearly visible, they are adjacent. These 4 cells are also adjacent. They are considered as adjacent cells. Similarly, these 4 cells are also adjacent cells. These 4 cells are also adjacent cells. Again, we can consider these two and these two, they are placed side by side if we make a cylinder out of these two lines. So these 4 cells are also adjacent cells. Finally, one unique feature of this 4 variable Karnaugh map is that all the corner cells 1, 2, 3, 4, they are adjacent cells. These 4 corner cells are adjacent cells. So here adjacent cells having 4 smaller rectangle and adjacent cell having 2 smaller rectangles are shown. Now let us see the adjacent cells for 8 smaller rectangle case. Let us take this picture left. We know 2 to the power 3 equal to 8. So we can take 8 smaller rectangle as adjacent cell. So if we take this 8 rectangle, they are adjacent. These 8 rectangles are also adjacent to each other. These 8 rectangles are also adjacent to each other. These 8 rectangles are also adjacent to each other. If we make a cylinder by connecting these two sides, these 4 and these 4, they are adjacent and they will make it 8. Again, these 4 and these 4 will make 8 and they are adjacent. Next, we will see the naming of the rectangles containing several adjacent cells. First of all, we know how to name a single cell in terms of product term and in terms of sum term. Suppose if you are asked what is the name of this cell, we have a equal to 1, b equal to 0, c equal to 0, d equal to 0. So 1, 0, 0, 0. So this has value 1, 0, 0, 0. In terms of min terms, we can write a, b prime, c prime, d prime. In min terms or in product term, our target is to make the output 1. So if we have a1, b0, c0, d0, then for these values a equal to 1, b0, so b prime will give you 1, c prime will give you 1, d prime will give you 1. Ultimately the ended value will be 1. In terms of max term or sum term, the same box can be expressed in this fashion: a prime plus b plus c plus d. Here our main target is to make the output equal to 0. If a equal to 1, a prime will give you 0, b equal to 0, c equal to 0, d equal to 0. Ultimately you will get 0. We'll express the boxes in terms of min term. If you are asked to express the box in terms of sum term, then take the invert of each variable of this product term and put OR sign in between. You will get the sum term expression. Now suppose we want to name this is a rectangle containing 2 adjacent cells. So what is the name of this? So we see this box is covered by this line and these 2 lines. Okay, this horizontal line and 2 vertical line. As this is a unique horizontal line and it has a equal to 0, b equal to 1, so directly I'll write a prime b, no problem. But for the vertical line, we have c equal to 0 in this vertical line and c equal to 1 in this vertical line, d equal to 1 in this vertical line and d equal to 1 in this vertical line. Now as we are getting all the values of c, that means c equal to 0, this box is true. For c equal to 1, this box is true. So whenever for any variable if the rectangle is true for all values of that variable, then we can ignore that variable, ignore writing that variable. So what is the value of d here? D equal to 1, d equal to 1. D equal to 0 is not valid for this box. So as c equal to 0, c equal to 1, both are true for this particular box, we can ignore c. And for d, d is equal to 1, so we'll write d. Now let us see the name of this rectangle, the blue one. Here a equal to 1, a equal to 1. These two horizontal lines and one vertical lines are covered. A equal to 1, a equal to 1, and b equal to 1, b equal to 0. B is having both the values 0 and 1. A is having 1. So we will write A. And we will ignore B as B is having both the values. B is ignored. Here in this vertical line, C equal to 1, D equal to 1. So we'll write C, D. So the name of the box in terms of product term is A, C, D. In terms of sum term, we can write A prime plus C prime plus D prime. And in terms of sum term, the name of this box can be written as A plus B prime plus D prime. I think it's very simple. Now let us find the notation of this red rectangle containing 4 adjacent cells. We have A equal to 0, A equal to 0, B equal to 0, B equal to 1, C equal to 0, C equal to 0, D equal to 0, D equal to 1. So we are covering 2 horizontal lines and 2 vertical lines. I repeat, A equal to 0, A equal to 0. So we'll write A prime as A equal to 0. B equal to 0, B equal to 1. So B is having both the values 0 and 1. So we can ignore B. C equal to 0, C equal to 0. We'll write C prime. D equal to 0, D equal to 1. So we will ignore D. So the name of this box is A prime, C prime. Let us see more examples. We'll take a new map. Suppose we want to name this box having 4 adjacent cells. We have 2 horizontal lines and 2 vertical lines. For the horizontal lines, we have A equal to 0, A equal to 1. Both the values of A is covered. We will ignore A. So the name of this box will be B equal to 0, B equal to 0. So we'll start from B prime. C equal to 0, C equal to 1. So we'll ignore C. D equals to 1, D equals to 1. So we'll write D. So the name of this box is B prime D. Let's see the naming of 8 adjacent cells. What is the name of this green box containing 8 adjacent cells? Here we need to consider 4 horizontal lines and 2 vertical lines. If we consider 4 horizontal lines, all the values of AB are true for these 4 horizontal lines. So A equal to 0, B equal to 0, A equal to 0, B equal to 1, A equal to 1, B equal to 1, A equal to 1, B equal to 0. So this green box is true for all the combinations of AB. That's why we can ignore AB. Now for CD, C equal to 0, C equal to 0. We'll write C prime. D equal to 0, D equal to 1. So these two lines are true for D equal to 0 and D equal to 1. Both the values of D, we can ignore D. So the name of this green box will be C prime. You can see the number of terms becomes less if you increase the number of adjacent cells. If you take only one cell, then all the variables will be there. If you take 2 cells, then 3 variables will be there for 4 variable case. If you take 4 cells, then 2 variables will be there. If you take 8 cells, then 1 single variable will be there. Now if you are asked to name this box containing 4 corner adjacent cells, this box is covered by 2 horizontal lines and 2 vertical lines. In this two horizontal line, we have a equal to 0, a equal to 1. So you can ignore a. B equal to 0, b equal to 0. So we'll write b prime first. Here, for this two vertical line, c equal to 0, c equal to 1. Ignore c. D equal to 0, d equal to 0. So we write d prime. So the name of these four corner cells is b prime, d prime. So far we have learned the mapping of Karnaugh map. We have got the idea on adjacent cells and naming the rectangles containing several adjacent cells. Now let us see some examples. How can we simplify Boolean algebra using Kernel Map Method? Then the concept will be very clear to all of us. Suppose we want to simplify this function f, x, y, z. That means there are three variables. Summation of min terms having 3, 4, 6, 7, these values. If we write this expression in terms of sum of min terms, what does 3 mean? 3 means 0, 1, 1. So we'll say x prime y z plus. What does 4 mean? 4 means 1, 0, 0. So x y prime z prime. What does 6 mean? 6 means 1, 1, 0. So x 1 y 1 0 z prime plus 7. What does 7 mean? 1, 1, 1 x y z. Now we can simplify this function using algebraic method and we'll get the result, but we'll simplify this function using Karnaugh map method. So if I write this as a value 0, 1, 1 1, 0, 0 1, 1, 0 1, 1, 1. As we have three variables, we need to go for three variables mapping. We can either take x, y in one side, z in another side, or we can take x in one side, z in another side. Let's take x in one side and y, z. So yz has 0, 0, 0, 1, 1, 0, 1, 1. These values, and x has 0 and 1 value. Now, while mapping, we need to put ones in each positions where the function is true. We have function f that is true for 0, 1, 1. We have 0, 1, 1 value here, so we need to put 1 here. 1, 0, 0 or x, y prime, z prime. We have x, y prime, z prime in this box. We need to put 1 here, or 1, 0, 0. In this way also we can put 1, 1, 0, 1, 1, 0. Here we need to put 1, 1, 1, 1, 1, 1, 1. So we need to put 1 here. We have completed the mapping of ones for some of midterm cases. Next, we need to take as bigger number of adjacent cells containing ones as possible. Suppose, let's see, can we take 4 ones which are placed in adjacent cells? No. We have 3 ones here, and we cannot take this 4 because we have a gap here. We cannot take 4 adjacent cells in other ways as well. So the bigger box containing 1 can be taken having 2 adjacent cells. How? We can take these 2 ones. This is the biggest box. Still we have these 2 ones. So we can consider these 2 as adjacent cell, and we can consider them in one rectangle. Now, what is the name of this rectangle? We have x equal to 0, x equal to 1. We can ignore x. We have y equal to 1, z equal to 1. So the name of this box is y, z. And what is the name of this box? We have x equal to 1. So write x here. For y, z, y equal to 0, y equal to 1. So you can ignore y. Z equal to 0, z equal to 0. We can write z prime. So the function, the simplified version of this function will become xz prime this plus yz. This is the simplified version, and this is represented in soft form. Let us see another example. Function x, y, z equal to summation of min terms 0, 2, 4, 5, 6. Let us take x, y in one side and z in another side. X, y, z, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1. So 0, 0, 0 will be here, 0, 0, 1 will be here. Now I'm not writing in sum of min terms form like this way. From here we can put ones. How? 0. 0 is having corresponding binary value 0, 0, 0. So here it will be 1. 2. 2 is having corresponding binary value 0, 1, 0. So we'll be having 1 here. 4. 4 is having corresponding binary value 1, 0, 0. 1, 0, 0 is here. 5. 5 is having corresponding binary value 1, 0, 1. So 1 will be here. 6. 6 is having corresponding binary value 1, 1, 0. So 1 will be here. Now what is the biggest set of adjacent cells containing 1 can be taken here? 4 adjacent cells can be taken. So let's take this 4 adjacent cell. Now we have remaining 1. In order to take the rectangle, biggest rectangle, for this one we can take the help of other ones even though they are covered by other rectangle. It doesn't matter, but we need to cover this one containing other ones, and by taking as many ones as possible so that the rectangle becomes as big as possible containing ones. So the biggest box we can take containing 2 ones. If it would possible to take 4 ones, then we would take 4 ones, but it's not possible because if we want to take this 2 as adjacent cell, as we have a gap here, so we cannot take like that way. So we need to confine with 2 adjacent cells. Now the naming. The name of this box is, this is true for all the values of x, y. So we can ignore x, y. And this is true for z equal to 0. So we'll write z prime. And the name of this green box is, this is true for x equal to 1, y equal to 0. So we'll write x, y prime. And this is true for z equal to 0, z equal to 1, ignore z. So the simplified version of this function in sum of product form, that means soft form, becomes z plus x, y prime. Let us solve another problem. Suppose we have a function f, a, b, c, 3 variables equal to summation of min terms 1, 2, 3, 5, 7. Now let's take a in one side, b, c in another side. A equal to 0, a equal to 1, bc equal to 0, 0, 0, 1, 1, 0, 1, 1. Now where to put ones? In 1. 1 means 0, 0, 1 here. 2 means 0, 1, 0. 3 means 0, 1, 1. 5 means 1, 0, 1. 7 means 1, 1, 1. Now what is the biggest box can we take containing ones? We can take 4 adjacent cells. This is the biggest rectangle we can take. Now for this one, what is the biggest box can we take? We can take 2 ones. Now all the ones are covered. Now let's start naming the boxes. What is the name of this blue box? We have a equal to 0, a equal to 1, ignore a. B equal to 0, b equal to 1, ignore b. C equals to 1, c equals to 1. So the name of the box is C. What is the name of this green box? We have a equals to 0, so write a prime, and b equals to 1, b equals to 1, so write b. C equals to 1, c equals to 0, ignore c. So the function in simplified form becomes c plus a prime b. I hope the examples are clear for 3 variable case. Let us solve some example for 4 variables case. Suppose we need to simplify a Boolean function having four variables w, x, y, z, which has sum of minterms 0, 1, 2, 4, 5, 6, 8, 9, 12, 13, 14. Here 0 means wxyz is having value 0, 0, 0, 0. 1 means wxyz is having value 0, 0, 0, 1. First, let's draw the four variable kernel map. We have wx here and yz here. 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 1, 1, 0. The location 0 is 0, 0, 0, 0. This is the location. We have 1. So 0, 1, 2, 3. These are the locations. 4, 5, 6, 7. Then this will be 8. 1, 0, 0, 0, 8. 9, 1, 0, 0, 1. So 8, 9, 10, 11, 12, 13, 14, 15. So if I write, this is 0th location 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These are the locations. Now let's start putting ones for which the sum of minterm is true. In the 0th location we have 1. In 1 location we have 1. In 2 location 1, 4. Here we have 1, 5. Here we have 1, 6, 1, 8. Here 1, 9, 12, 13, 14. The mapping of the ones is over. Now let us take the biggest box with the adjacent cells containing ones. We can take 8 adjacent cells. So we can take these 8 adjacent cells. Now for these 3 ones, we cannot take 3 together because either we need to take 2 or 4. Now, can we take 4? Yes, we can take 4 side by side. These ones are covered by another box, but if we can take these ones to make the other remaining ones having greater box, then we must consider that. Otherwise, the function will not be the simplified version. Finally, for the single one, what is the maximum number of ones can we take? We can take 2 or we can take 4 even. So we'll go for 4. So we'll take these 4 adjacent cells. Now let us start naming the boxes. The name of this box is, all the combinations for wx is true for this purple box. So we'll ignore wx. Now here, these 2 vertical lines covering this purple box. So y equal to 0, y equal to 0. So we'll write y prime. Z equal to 0, z equal to 1. So we'll ignore z. Now let's name this red box. What is the name of this red box? We have w equal to 0, w equal to 0. So we'll write w prime. X equal to 0, x equal to 1. Ignore x. Y equals to 0, y equals to 0. So we'll write y prime. Z equal to 0, z equal to 1. Ignore z. Now let's name this green box. Name of this green box is, we have w equal to 0, w equals to 1, ignore w, x equal to 1, x equal to 1, so write x. We have y equal to 0, y equals to 1, so ignore y. We have z equal to 0, z equal to 0, so write z prime. So the naming of all boxes is done. So the simplified version of this function becomes y prime plus xz prime plus w prime y prime. This is in sum of product form. Now, if you are asked to find the complement of this function f, that means f prime, in sum of product form, how to solve it? Once you put ones for this function, the remaining boxes will contain 0. So let's put zeros here. So we have zeros here. Now, if you want to express this function in complemented form, then you must map these zeros. In order to get the simplified version of the function, you need to map the ones. In order to get complemented function, you need to map the zeros. So let us map zeros. We can take this 4. Now for this remaining 0, we can take this 2. This is the biggest box we can take. Now name of this orange box is, we have all the combinations for wx, so we can ignore wx. We have y equal to 1, z equal to 1, so we'll write y, z. And the name of this blue box is w equal to 1, x equal to 0, so wx prime, y equals to 1, y equals to 1, so we'll write y, z equals to 1, z equals to 0, so we will ignore z. Now the complement of this function f prime, w, x, y, z, in simplified SOP form can be written as yz plus w, x prime, y. This is also in soft form. Here I made a mistake while naming the red one. W equals to 0, w equals to 0, so we'll write w prime, x equals to 0, x equals to 1, ignore x. In these two lines, y equals to 0, y equals to 1, so we will ignore y. Z equals to 0, z equals to 0, so we'll write z prime. So this will be w prime, z prime. Now let me brief the whole process. If you are asked to simplify any function, just put ones for these functions. If the function is given in terms of min terms, and map the ones, you'll get the simplified version in soft form. Now if you want to get the complement of that function in soft form, map the zeros and you will get the simplified version of the complemented function in SOP form. Next we will see the simplification of any functions in POS form, that means product of sum form. Suppose we want to simplify this same function that we used in previous example. First you may map the min terms, that means the function given by this. We have 0, 1, 2, 3. 3 is not there, that's why I'm not writing any number here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is the mapping for 1. As it is in min term, the targeted value is 1, that's why we are placing ones here. So the remaining boxes will be filled by zeros. Okay. Now if we map the ones as we knew from our previous example, we'll get the simplified version of this function f. But if we map the zeros, we'll get the simplified function of complemented f, that means f prime, in SOP form. So let us map these zeros. We have one box here and another box is here. Now the name of this black box is, this is true for all the combinations of wx, so we can ignore wx. Y equals to 1, z equals to 1, so this will be yz. And the name of this red box is wx prime y. So we can say f prime of wx y z can be written in soft form yz plus wx prime y. Now if we take the complement of this f prime function, then we'll get f prime whole prime, that will eventually return us f, and here we can write yz plus wx prime y whole prime. So this can be written as f, which is equal to yz using De Morgan's theorem prime into wx prime y prime. Again, if we apply De Morgan's theorem, we'll get y prime plus z prime w prime plus x plus y prime by applying De Morgan's theorem again. Now this is the function expressed in pos form. So we have function f equals to y prime plus z prime multiplied with w prime plus x plus y prime. So they are expressed in pos form, and this is the most simplified version. This is one of the ways how you can express your function in pos form. So this is in pos form. Let me show you another method by which you can get the pos form of any function directly. If we take the same example, let's map this example. If we map the ones from the previous example, we are directly putting the ones using this function, and these will be the zeros. Now if you want to get the simplified version of any function in pos form directly, what you can do, you can map the zeros. So let's map the zeros. These are the two boxes we can take. Name of this box in product form, we know it is YZ. But if we want to name this box in sum form, then this name will be y prime z prime, which was shown in the previous examples. Now again, the name of this orange box in product form, we know this is wx prime y, so I'm not writing it here. And the name of this box, same box, in sum form, we can write, we have w equals to 1, so we'll write w prime. X equals to 0, so we'll write plus x, and we have y equals to 1 and y equals to 1, so we'll write y prime. We have z equals to 1, z equals to 0, so we will ignore z. So this is w prime x plus y prime. So the simplified version of this function in pos form can be written as y prime plus z prime multiplied with w prime plus x plus y prime. Let me repeat the procedure. If you are given a function in sum of minterms form, this is sum of minterms form, and you are asked to express the simplified version of this function in pos form. So what you can do, you can map the ones from this sum of minterms form. We can map the ones. Then remaining boxes will be for 0. Then map the zeros. Once you map the zeros, name the boxes in sum form, not in product form, sum form and sum form. Finally, write the function by writing each sum form inside the bracket, and all these sum forms will be placed in multiplied form to express the function in product of sum form or pos form. Now we will see an example. If the function is given in product of max term form, how can you simplify the function in SOP and POS form? Suppose a function is given in product of max term form where we have 4 variables a, b, c, d. If we write the function in product of max term form, we'll get, we have 0. For 4 variables, 0 means 0, 0, 0, 0. Whenever a equals to 0, b equals to 0, c equals to 0, d equals to 0, the targeted output is 0 for max term form. We know this. So we'll write a plus b plus c plus d. Now for 2, the values for a, b, c, d are respectively 0, 0, 1, 0. So we can write a plus b 0, 0 plus 1 means c prime plus d. Now for 4, it's 0, 1, 0, 0. For 8, we can write a prime plus b plus c plus d. It's 1, 0, 0, 0. For 9, it's a prime plus b plus c plus d prime. For 12, it's 1, 1, 0, 0. A prime plus b prime plus c plus d. So this is the function in product of sum form. We will simplify this function using Kernel Map method. Let us draw the box first. A, B, C, D. 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. Now, if we want to map this max term forms, we know the targeted value for max term is 0. The targeted value or targeted outcome for each min term is 1. That's why we placed 1 for each values or each positions. Now, as it is expressed in product of max term form, so for the positions mentioned here, we will place zeros. We have 0, so we'll place 0 here, then 2, 0, 1, 2, this is the 2 position, so we'll place 0 here, 3, 4, this is the 4th position, 0, 1, 0, 0, which means 4. So in 4th position, as it is product of max term form, we will place 0 here, 4, 5, 6, 7, then 8, then 9, 10, 11, 12, 13, 14, 15. Now placing of the values for this function is over. Remaining boxes can be filled by the complemented value of this 0. So we can fill those boxes by 1. Now the method is very simple. First of all, you want to express the simplified version in soft form or pause form. You need to decide. If it is asked in the question that you need to express simplified function in pause form, then map the zeros. If you want to express the simplified function in soft form, then map the ones. So let's express this function or simplified function in pause form first. So we'll map the zeros. We have one box. This is the second box we can take. Still one box is remaining. Now the namings. The name of this blue box is, definitely we need to write in sum form. So we have C equals to 0, D equals to 0. We'll write C plus D. Next name of this box is, we have A equals to 1, B equals to 0. So we'll write A prime plus B. C equals to 0, C equals to 0. So we'll write plus C. D equals to 0, D equals to 1. So we will ignore D. So this is the name of this sky blue box. Now let us name this orange box. A equals to 0, B equals to 0. So A plus B. C equals to 0, C equals to 1. Ignore C. D equals to 0, D equals to 0. So write plus D. So the simplified version of this function becomes A plus B plus D whole multiplied with A prime plus B plus C whole multiplied with C plus D. This is the function expressed in pause form. Again, if you want to express the same function in soft form, in simplified way, then you need to map the ones. Let's solve it. We can take 4 boxes together. We can take another 4 boxes. Now for this one, we need to take this 4 boxes. Finally, for this one, we need to take this box. Now let's go for the naming. The name of this red box is A equals to 0, A equals to 0. So it will be A prime. We must write it in product form. B equals to 0, B equals to 1, ignore B. C equals to 0, C equals to 1, ignore C. D equals to 1, D equals to 1, write D. Name of this box is B, C. Name of this box is A, C. Finally, name of this box is B, D. So the simplified version of this function in soft form becomes A prime D plus BC plus BD plus AC. This is in soft form. Next, we will learn simplification with don't care condition. Before we go for the simplification, first we need to know what is don't care condition. For certain input cases, we'll find while implementing any circuit or while designing any circuit, for certain number of inputs, we don't care about the outputs because the output does not depend on those input sets. Let me show you an example. Suppose when we consider the BCD case, we know 0, 0, 0, 0 represents 0, decimal 0. So this is BCD. 0, 0, 0, 1 represents decimal 1. 0, 0, 1, 0 represents decimal 2. In this way, 1, 0, 0, 0 represents decimal 8 and 1, 0, 0, 1 represents decimal 9. Now, if we have these four inputs, A0, A1, A2, A3, using 4-bit, I can have 16 combinations, but we know for representing these decimal numbers, these are decimal numbers, we will have up to this combination, that means 1001. Now, if we want to represent 10, how can we represent 10? So we'll write 10 here. 0 is represented by 0, 0, 0, 0, and 1 is represented by 0, 0, 0, 1. So we can say the number that we are having 1, 0, 1, 0. Let us take this portion a bit. 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and finally 1, 1, 1, 1. These combinations will never occur. So we can say these input combinations will never come. That's why they are don't care conditions. Don't care. We don't care about these inputs because these inputs will never come. We have numbers starting from 0 to 9. So in order to represent 10 or 11 or 12, we'll utilize these combinations. So after 1001, 1010 will never come. So as they will never come, we don't care about these combinations. If we consider the don't care combinations, the circuit becomes less complicated. I'll show you the practical examples later on, but first you see how to simplify any function with don't care condition. Suppose a function is given where f, a, b, c, d, that means there are 4 variables, is having summation of min terms 1, 3, 7, 11, 15. And the don't care condition a, b, c, d is given in summation of min terms having 0, 2, 5. Now, how to simplify this function considering don't care condition and without considering don't care condition, we'll see this. Let us map the ones for this function. We have 1 in first position, that means 0, 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now let us place the don't care condition. The don't care condition will be placed with a symbol neither 0 nor 1. So we'll place cross sign for the positions of don't care conditions. At 0th position, we'll place cross because it's don't care condition. 2, here we'll place cross. 5, here we'll place cross. Once the don't care conditions and other mappings, 1 mappings are done, remaining boxes will be filled by zeros. Now let us simplify this function without considering the don't care condition. Let's map the ones. We can take this bigger box and we can take this box. Name of this red box is CD and name of this blue box is A prime, B prime, D. So the function can be written in terms of soft form f, a, b, c, d. A prime B prime D plus CD. This simplification is done without considering don't care condition. Now, if we want to use the don't care condition for the simplification, you need to remember we can take the help of these don't care conditions for making the box size of containing ones as big as possible. We do not care about the remaining don't care conditions, but if we need, we can take the help of these cross signs or don't care conditions. And this help can be taken by ones as well as zeros. For example, for finding f prime, if we need to take the help of this cross, then it can be merged with zeros and it can be merged with 1. Let's see the simplification process considering don't care condition. For the same functions, we'll find this simplified expression. Now, if we consider the don't care condition while taking these 4 ones, even though if we want to take the help of x, we cannot take bigger box, we cannot take 8, so these 4 will be taken. Now, for this remaining one, what is the size of the box can I take? We can take 2 boxes containing ones, but as I told you, in order to make the box size bigger, we can take the help of x. So we can make the box size containing 4 cells. Now, even though we have 2 don't care conditions left, we do not have to care about those don't care conditions. We'll consider about the ones while finding the function in subform, or we'll consider the zeros while finding the complement version of the f function. Now, if necessary, this x can be merged with zeros as well. Now, the name of this red box becomes CD and the name of this green box becomes A prime D. So the function becomes f A B C D, considering the don't care condition, A prime D plus CD, which requires less number of gates to implement than this one. Now, if we want to find the complement of this function, considering the don't care condition, we can map the zeros. So if we want to map the zeros, we can take 8 smaller cells by taking help of the don't care conditions. And for the remaining 2 zeros, we can make this box containing 4 cells. So the f prime A, B, C, D can be written as D prime plus A C prime. I hope it is well understood.